Unsupervised learning, on the other hand, looks at unlabeled data and looks for hidden structures. So it looks at patterns that clusters customers together or clusters records together to try to find useful patterns in that data. A good example that we can touch and feel on a daily basis, God forbid for anybody listening, cancer, for example, cancer detection, and looking at data coming, patient data coming, whether it's in real time or historical, and start to predict when, like cluster common traits for cancer patients versus non-cancer patients, cluster common traits for people that are likely to default in their loan versus others that are not likely to default on their loan. Many different, I mean, you can think of the applications across so many different industries for unsupervised learning. And it's one of those things that we looked at to leverage this amazing set of data that the organization has had. And before the discipline of AI and bringing machine learning and unsupervised learning, all that data was just collecting dust and just, sucking air, but there was nothing really happening with it. Now we can use that with unsupervised learning to actually start extracting more insights and say, hey, these customers look like they behave similarly, and these customers behave similarly. You can even go as far as saying, here's 1 million customers. Look at these and try to tell me how many clusters you can create from these customers, like grouping of similar traits. And then it actually gives you an elbow curve where you could actually see it saying, all your customers, this is like no segmentation, 0 segments or 1 segment, all the customers the same. And it starts going down to this elbow curve where you can actually, as a scientist or as an AI researcher or AI practitioner, you can look at this curve and say, okay, if I use 5 or 6 segments, I can actually take those 1 million records and I can segment them into 5 or 6. And the curve goes on. But the point of unsupervised learning is that there isn't really much that needs to be done on that data rather than simply running a machine learning algorithm to say, go cluster these people and tell me how many, what's going to be the population or what's going to be the number of records per cluster based on the size of the cluster. And it can actually give you visualization to help you even pick the clusters. It's super cool, unsupervised learning. Reinforcement learning, we've touched on quite a bit with several other, like in the generative AI, we talked about reinforcement learning with human feedback, RLHF, where, again, today we talked about it a bit, where we remove bias, we try to create a balanced algorithm, we try to remove anything that could be harmful. So it's a way to reward or penalize the algorithm by making sure that we bury bad output and we reinforce and reward good output. And today, if anything I learned from today's conversation with everybody is that is subjective, of course, and it depends on the humans that are doing the RLHF. But we're just saying, we just need an average. Like, you're not based on where you are, what country, and what's the cultural norm. Things will be different and they'll change. But the concept of reinforcement learning is about having reward and penalty for output, which teaches the neural network to say, don't generate more like this, generate more like this. And that's what reinforcement learning is all about. Any questions on this slide before I move on? Awesome, no one is typing. So you understand what's going on, or I've just put you to sleep, one of the two. So let's take a look at the comment. As I said, we're going to focus on supervised learning. The intention for today is to pique your interest, hopefully give you an umbrella view understanding of machine learning, and actually kind of hopefully open up your horizons to the potential of being able to take data sets from the internet and start actually playing with it without being scared or freaked out, and just seeing the sheer awesomeness of what you can do today versus like when I did the course at Stanford for machine learning for like 9 months or whatever. It was all coded manually. We had to do linear algebra, derivatives, and matrices, and all this stuff that now you can do with Google Colab and generative AI was beyond reach, not because I'm not saying anyone is like not capable or not. It's just there's no interest. It's too complicated, right? Now it's become much, much, much easier and much, much more accessible, as long as you have the curiosity and the willingness to sweat a little bit and try, kind of venture into the engineering world. It's not hard. It's just a matter of trial and error and working with your generative AI models to start really understanding the different lines of code. There's a lot that you can do. There's a lot that you can do out of the box. So let's take a look at the different algorithms. We're really going to focus on, I really want to focus today on linear regression, but you have, and I'll ask Hazar to get these slides, we'll PDF these slides or whatever, upload them on the microlearning series with the video, so you'll have access to them. But when I focus on linear regression, it's about predicting continuous outcomes, sales forecasts, housing prices, anything that's numeric that has a lot of pairing of features and then labeled, like labeled data or labeled output. Linear regression is very good at this, and it tries to create an average across all of these values and it's called linear regression because it looks like it's a slope that starts, if you look at the X and the Y based on what your values are, usually it's a slope that starts from the lower end based on what your parameters are and what's the output value, and then it kind of goes straight through, and it is linear. Usually it's a straight slope and it's sloping up and headed that way because, as these parameters change, then the price change or whatever that forecast is, you'll see like a lot of bubbles with a line running across, and it's called linear regression. Logistics regression, in contrast, is binary. It is either, it's like fraud detection. It's either yes or no. It's this or this, yellow, green, or blue. There's no middle ground, or this is a 35.5. That's not what logistic regression is. Classification. And it looks at probabilities of what something could be, this class or that class. And when it crosses over a certain threshold, it'll declare that it's that class. So probabilities and coefficients interpretable, let's just leave it alone. And then you could see this performance, and the reason for this performance is just to indicate in production, high throughput systems, what is the performance and the capability of these. Linear regression is mathematically intensive. It's a lot of matrix multiplication, a lot of linear algebra, and it's a lot of gradient descent features. Anyway, it doesn't matter, but all that stuff takes compute and it takes time. And as you see, as you go further down, like decision trees and random forests, actually they are optimized for high performance for the types of use cases. I'm not going to go through these. Other ones you can look at them: support vector machines, neural networks, etc. And you can do the reading and you can do your own kind of investigation of those. Today, we're really focused on linear regression.